Recall the power of a quotient rule for exponents. So if you have a quotient raised to a power, then the numerator gets that power, the denominator gets that power. We could also go backwards, right? Start with the quotient where they have the same exponent, put them in a quotient with the same exponent. So that's what we can do with the quotient rule for radicals as well. If you have a single radical with a quotient, you can split that radical up into two separate radicals, one for the numerator, one for the denominator, and they will also have the same index. So let's use that quotient rule to simplify radicals here, assuming that all variables represent positive real numbers, and that's so we don't have to worry about absolute values. So our first example, the square root of 9/25. I could probably figure this out without separating them, but I can also separate. So I can have the numerator have its own radical with the square root index, and the denominator have its own radical with the square root index, and then I can look at those separately. So in the numerator, the square root of 9, that's got to be 3 because 3 times 3 is 9. And the square root of 25 in the denominator, that's 5 because 5 times 5 is 25. So that'll be my simplified expression there. For b, this one I have to break up into separate radicals because the numerator doesn't have a square root. It's, well, what times what equals y? That might be a bit difficult. So let's split those up. So that'll be the square root of y in the numerator and the square root of 36 in the denominator. Because there is a square root of 36. 6, because 6 times 6 is 36. So that's the root. And in the numerator there is no square root y. So it stays square root y. And that's the simplified expression. I'm going to continue to use the quotient rule here. So c, the cubed root of 27/64. Again, I could probably do that without separating, but I can also separate by the quotient rule. So the numerator has its own radical with an index of 3, and the denominator has its own radical with an index of 3. Then the numerator, the cubed root of 27, that's got to be 3, because 3 times 3 times 3 is 27. And in the denominator, the cubed root of 64 is going to be 4, because 4 times 4 times 4 is 64. So the simplified expression is 3/4. For d, I'm going to have to use this quotient rule, because again, it's not going to work out otherwise. So I'm going to have two separate radicals, one in the numerator, one in the denominator. They both have an index of 5. The index must be the same. So in the numerator, you only have 7. In the denominator, we have 32x to the 5th. So in the numerator, I can't simplify that. There's one factor of 7. I need 5 factors to have a perfect root. So nothing's happening in the numerator. It's going to stay 5th root of 7. But in the denominator, we can simplify that. I could break those apart into separate radicals by the product rule if I want. So the 5th root of 32 times the 5th root of x to the 5th, if you want to look at it that way. And then we can continue simplifying that in the denominator. So 5th root of 32, well, what number times itself 5 times is 32, and that's 2. So that's the root. And the 5th root of x to the 5th, that's like the nth root of a to the n, right? So it cancels the radical and the exponent at the same time, and it leaves just the x, the base there. And I don't need an absolute value because it's odd and because this represents all positive real numbers, so not worried about that at all. And that would be my simplified expression.